Good morning, students. This is Addagatla Nagaraju, working as lecturer in electrical and electronics engineering, Government Polytechnic, Station Rampur. Today, we are going to learn briefly fourth semester's AC machines subject. So, in that single phase transformers chapter, we are covering. So, in single phase transformer, E.M.F equation of a single phase transformer, transformation ratio, problems on E.M.F equation of a transformer, topics we will cover in this chapter. E.M.F equation of a single phase transformer, transformation ratio, problems on E.M.F equation of a transformer. So, in the previous class, we have learned about working principle of transformer, classification of transformer, construction details of a transformer, comparison between core and shell type transformer we had discussed. Working principle, Faraday's law of electromagnetic induction and mutual induction. Classification based on number of phases, single phase, polyphase, based on physical construction, core type, shell type, battery type, based on cooling, oil, dry, different types of classification we had discussed in the yesterday's class. Construction details of a transformer. The core is laminated, core is made of silicon steel, to CRGO steel, and two windings transformer, single winding transformer is auto transformer, winding copper material we had discussed, and comparison. Core and shell type. Core is for low voltage, shell type for high voltage. We had discussed in the yesterday's class. Coming to the today's class, on completion of this period, you would be able to derive the E.M.F equation of a transformer. Derive the E.M.F equation of a transformer. Understand the transformation ratio and solve problems on E.M.F equation. You would able to solve the problems, you will be able to understand the transformation ratio, you will be able to derive E.M.F equation of a transformer. Theory of an ideal transformer. Time permits, we will cover ideal transformer also. And a practical transformer working on no load. Vector diagram for the ideal and practical transformer on no load. Okay. So coming to the E.M.F equation of a transformer, primary winding of transformer is excited with alternating current or AC supply. Primary winding of transformer is excited with alternating current or AC supply. This is the AC supply. This produces alternating flux and current as shown in the figure. Alternating flux. Let N1 is equal to number of turns of primary winding, N2 number of turns of secondary winding, V1 primary voltage, that is applied voltage, V2 secondary voltage, that is load voltage. Primary, N1 number of turns, here N2 number of turns secondary. V1 is the primary voltage, that is the applied voltage. V2 is the secondary voltage, that is the load voltage. E1 and E2, E1 and E2 are the induced EMFs in primary and secondary winding. E1 and E2 are the induced EMFs. Phi m is the maximum value of flux in Webers. Maximum value of flux. This is in Webers. That is equal to Bm into A. Where Bm is the flux density, A is the area of cross section. F is the supply frequency in hertz. F is the supply frequency in hertz. As shown in the figure, the frequency increases, the flux increases from zero, its zero value to maximum value phi m in 1/4 of the cycle, that is 1/4 of the cycle. This is the total time period, that is equal to 1 by f. This is the quarter, 1/4 f. In this quarter time period, flux is increased from 0 to 5 max, maximum value of the flux. Average rate of change of flux is equal to d phi by dt. Rate of change of flux, d phi by dt. The d phi flux changes 0 to phi m, that is called phi m minus 0. Phi m by dt, time changes 0 to 1/4 f. So phi m by 1/4 f, that is equal to 4f phi m volts. Rate of change of flux is equal to 4 into f into phi max. 4 into f into phi max. According to Faraday's law of electromagnetic induction, rate of change of flux means EMF induced in volts. Therefore, average EMF per turn is equal to 4 into F into phi m, since flux varies sinusoidally. 4F phi m for 1 turn. Form factor is equal to RMS value by average value, because it is a sinusoidal flux. Form factor is equal to RMS value by average value. We need RMS value. RMS value is equal to form factor into average value. Form factor is equal to 1.11, average value is equal to 4F phi m. We know. RMS value of EMF per turn is equal to 1.11 into 4F phi m, that is equal to 4.44 F into phi m. RMS value of induced EMF in primary winding P1 is equal to N1 into 4.44 phi m into F. 4.44 F N1 phi m. Similarly, RMS value of induced EMF in the secondary winding 4.44 F into N2 into phi m. Coming to the transformation ratio. The ratio of secondary voltage to primary voltage is known as transformation ratio K. Secondary voltage to primary voltage is known as transformation ratio. It is represented by the letter K. K is equal to V2 by V1. An ideal transformer V1 is equal to E1, V2 is equal to E2. Therefore, hence, the voltage ratio, that is the transformation ratio, K is equal to V2 by V1, that is equal to E2 by E1. 4.44 F N2 5M by 4.44 F N1 5M, that is equal to N2 by N1. Therefore, transformation ratio K is equal to V2 by V1 or E2 by E1 or N2 by N1. If V2 greater than V1 or N2 greater than N1, then K greater than 1, the transformer is called a step-up transformer. If V2 less than V1 or N2 less than N1, then K less than 1, then the transformer is called a step-down transformer. The transformer is called a step-down transformer. Current ratio. An ideal transformer losses are negligible, hence output is equal to input. Therefore, V2 into I2 is equal to V1 into I1. I2 by I1 is equal to V1 by V2 or N1 by N2 or E1 by E2, that is equal to 1 by K. Current ratio is inverse to the transformation ratio. Current ratio is inverse to the transformation ratio. We will see one example. A single phase transformer has 350 tons primary and 1050 secondary tons. The primary is connected to 400 volts 50 Hz AC supply. If the net cross-sectional area of the core is 50 centimeters square, calculate the maximum value of flux density in the core and the induced E.M.F in the secondary winding. Maximum value of flux density in the core and induced E.M.F in the secondary winding. So, given number of primary turns N1 is equal to 350. Number of secondary turns N2 is equal to 1050. Voltage applied to the primary 400 volts. Primary induced EMF also 400 volts. The net cross-sectional area 50 centimeters square, that is equal to 50 into 10 to the power of minus 4 meters square. Supply frequency 50 Hz. Find out BME2. BME2. Okay. So we know that primary induced EMF E1 is equal to 4.44 F N1 5M, that is equal to 4.44 F N1 V max into A, that is the E1 value 400 given. Maximum value of flux density in the core B max is equal to E1 by 4.44 F N1A. E1 is equal to 400 by 4.44 into F is equal to 50, N1 is equal to 400, A is equal to 50 into 10 to the power of minus 4. If you calculate, you will get 1.0296 Weber per meter square or Tesla. Webers per meter square or Tesla. Secondary induced EMF E2 is equal N2 by N1 into E1, that is equal to 1050 by 350 into 400. E2 is equal 1200 volts. E2 is equal 1200 volts. A 500 kVA 11,000 by 400 volts 50 hertz single phase transformer has 100 turns on the secondary winding. Calculate the approximate number of turns in the primary winding, the approximate value of the primary and secondary currents, the maximum value of the flux in the core. Given data, rating of the transformer 500 kVA, primary applied voltage V1 is equal to 11,000 volts, secondary voltage V2 is equal to 400 volts. Number of secondary turns N2 is equal to 100. Number of primary turns N1 is equal to N2 into E2 by E1. Find out N1, I1, I2, phi max. Approximate number of primary turns N1 is equal to N2 into V1 by V2, that is equal to 100 into 11,000 by 400. 11,000 by 400. Therefore, N1 is equal to 2,750. 2,750. Full load primary current I1 is equal to rated kVA into 1000 by V1, that is equal to 500 into 1000 by 11,000. 45.45 amperes. Full load secondary current I2 is equal to rated kVA into 1000 by V1, that is equal to 500 into 1000 by 400, that is equal to 1250 secondary. 1250 is the secondary amperes. Primary induced EMF E1 is equal to 4.44 F into N1 into phi m, that is equal to V1. Maximum value of flux in the core phi m is equal to E1 by 4.44 F into N1, that is equal to 11,000 by 4.44 into 50 into 2,750, that is equal to 0.018 webers. Next problem. A single phase 600 by 230 volts 50 hertz transformer has a core area of 400 centimeters square and a maximum flux density of 1.18 Webers per meter square. Calculate the number of turns in primary and secondary windings. Number of turns in primary and secondary windings. Given voltage applied to the primary E1 is equal 6600 volts. Secondary voltage E2 is equal 230 volts. Supply frequency F is equal to 15 Hz. Core area A is equal to 400 centimeter square. That is equal to 400 into 10 to the power of minus 4 meter square. Maximum value of flux density 1.18 Tesla. Find N1, N1 and N2. Flux in the core phi1 phi m in the is equal Bm into A. That is equal 1.18 into 400 into 10 to the power of minus 4 Webers. Primary induced EMF E1 is equal 4.44 F into N1 into phi m. Primary turns N1 is equal to E1 by 4.44 into F into phi m. It is equal 6600 by 4.44 into 50 into 1.18 into 400 into 10 to the power of minus 4. It is equal to 630. Secondary induced EMF. Secondary induced EMF E2 is equal to 4.44 F into N2 into phi m. N2 is equal to E2 by 4.44 F into phi m. 230 by 4.44 into 50 into 1.18 into 400 into 10 to the power minus 4. That is equal to 22, 22 tons. Coming to a theory of ideal transformer. An ideal transformer is one whose output is equal to the input. So, theory of ideal transformer. An ideal transformer is one whose output is equal to the input. That is loss-free transformer. Loss-free transformer. The transformer is called an ideal transformer if it is satisfy the following properties. It has no iron losses, that is hysteresis and eddy current losses in a transformer core are zero. Windings have zero resistance, that is, there is no ohmic power losses and no resistive voltage drop. Leakage flux is zero, that is 100% full flux produced by primary winding links with the secondary winding. Permeability of core is high, that is negligible current is required to establish the flux. Efficiency is 100%, that is the power input is equal to power output. Practically, no transformer is ideal, but knowledge of ideal transformer helps us to develop the concept of behavior of practical transformer. This is the ideal transformer on no load. Consider an ideal transformer shown in the figure. Let the primary supply voltage V1. There is no load on the secondary, therefore I2 current is zero, that is secondary open. To produce flux, a small current is applied on the primary side. As windings are purely reactive, the current I1 lags the V1 by 90 degrees. This is the V1, this is the current, lags current. The current is called a magnetizing current, which magnetizes the core. You can magnetizing current, which magnetizes the core. Ideal transformer on no load. So when we apply the V1, the current lags the V1 by 90 degrees and the flux is follows the current, that is the I naught, that is the I mu. Now E.M.F induced in the winding primary and secondary E1 and E2 lags the current by 90 degrees. So E1 and E2 are opposite to V1. For currents, we are taking this E1 upside minus E1. The magnetizing current I mu is always in phase with the flux phi m. The varying flux is linked with the both windings, and so E.M.F induced in the primary and secondary E1 and E2 will lags behind the flux by 90 degrees. Lags behind the flux by 90 degrees. The E.M.Fs E1 and E2 are the in phase with each other. Magnitude of induced E.M.F in the primary winding will be even approximately E2 equal but opposite to the applied voltage V1 and is known as counter E.M.F or back E.M.F. The secondary voltage V2 is equal to E2 as there is no voltage drop in the secondary winding. Phasor diagram shown on the left side. Flux is common to both primary and secondary winding, hence taken as a reference to draw the vector diagram. When an AC supply is given to primary side of transformer and the secondary terminals are left open, the primary winding takes very small current known as no load current I0 as shown in the figure. V1 I0, this is the I0. So no load current I0 is usually 2 to 5% of full load current, which produces flux phi m in the core. A part of the current I0 will, however, be spent on supplying iron losses in the core, that is the working component IW. Small amount of copper losses. I naught square R1 in the primary winding, there being no copper loss in the secondary as it is open. Alternating flux phi m will induce an E.M.F in the primary and secondary winding. E1 and E2 are in the face each other. The induced E.M.F will lag behind the flux by 90 degrees. To the given, there is a phi m. This is I0, two components, working component and magnetizing component. Okay. Working and magnetizing component. E.M.F lags flux by 90 degrees, that is the E1 and V1. The no load current I0 taken by the primary consists of two components, a reactive or magnetizing component I mu producing the flux and hence in phase with the flux. An active or working component IW supply in the iron losses and the negligible copper losses in the primary winding. IW is in phase with the supply voltage by V1. I naught is equal to two components, IW and I, working component and magnetizing component. Therefore, I naught is equal vector sum of IW and I mu plus IW. Therefore, no load current I naught is equal under root I mu square plus IW square, I mu square plus IW square I naught is equal to under root I mu square plus IW square. Phasor diagram for no load condition is as shown in the figure. So no load current I naught lags the supply voltage V1 by an angle I naught. So cos phi naught is equal to no load power factor. Active or working component IW is equal to I naught cos phi naught. Reactive or magnetizing component I mu is equal I naught sin phi naught. No-load primary copper losses are negligible, hence the no-load primary input power is equal to the iron losses occurring in the core of the transformer. No-load input power W naught is equal to V1 cos phi naught, that is equal to V1 IW, V1 IW. Okay, coming to the summary, we have discussed about derivation of E.M.F equation of a transformer, that is equal to 4.445 Fn1. E1 is equal to 4.445 N1 F. Phi is the maximum value of flux density. E2 is equal to 4.44 F into N2 into phi n. The transformation ratio K, V2 by V1 or N2 by N1 or V2 by V1. And also problems solved on E.M.F equation of a single phase transformer. E.M.F equation of a single phase transformer. And also we have discussed about theory of an ideal transformer, practical transformer on no load, vector diagram of transformer at no load. We have discussed about theory of ideal transformer, practical transformer on no load, vector diagram of transformer at no load. We come into the quiz. E.M.F equation of a transformer is given by option A 4.44 F N1 phi n and 4.44 F N2 phi n. Option B 4.44 F into N1 and 4.44 F into N2. C none of the above. So answer 4.44 F into N1 into phi n for primary. For secondary, 4.44 F into N2 into phi n. Okay. The transformation ratio of a transformer is given by option A V2 by V1, option B N2 by N1, option C I1 by I2. Option D all of them. So transformation ratio K is equal to V2 by V1 or E2 by V1 or N2 by N1 or I1 by I2. So answer all of the above. For step-up transformer, the transformation ratio K is option A less than 1, option B greater than 1, option C equal to unity, option D none of the above. Step-up transformer transformation ratio K is equal V2 by V1. For step-up, V2 greater than V1. Therefore, V2 by V1 is greater than 1. Greater than 1 per step. Per step term, less than 1. Okay? Answer greater than 1. An ideal transformer is said to be loss-free transformer. True or false? Ideal transformer is said to be loss-free transformer. Yes, it is true. Loss-free transformer. The no-load input of the transformer is practically equal to option A iron losses, option B copper losses, option C copper and iron losses, option D none of the no-load input of the transformer is used to supply both iron and copper losses. Both iron and copper losses. No-load input of the transformer is fractionally equal to iron losses. Okay. Because copper losses are negligible. Because secondary is open circuit, primary is supplied to magnetizing losses. But small amount of copper losses, hence we can neglect. Hence we can neglect. Coming to the frequently asked questions, explain in detail theory of an ideal transformer. Draw and explain no-load vector diagram of a single-phase transformer. Define magnetizing component and working component of no-load current. No-load current. Derive E.M.F equation of a transformer. Derive E.M.F equation of a transformer. Okay. So, if you have any doubts, you can contact me through my WhatsApp number 9866930004. Thank you.